Okay. Last week's practical completed solutions are available on on GitHub. So could you please check it? I noticed that some students do not check the update. So please do check it. I usually update it over the weekend. Okay, for this week, you must have learned some of units, all of Unit 9 and Unit 10, especially how to compute integrals and gradient descent algorithm. Okay, I hope you're familiar with those. The first question is about the Rayleigh distribution, which is a continuous distribution, probability distribution on non-negative random real numbers. The notation is X is distributed with Rayleigh with parameter sigma, where sigma is the shape parameter. The probability density function PDF is given by this expression here when X is positive, when X is non-negative, and 0 otherwise. The first question is plot the PDF of X for given sigma values, shape parameters. This is like using last week's code. I only changed the name of the distribution. Okay, last week we had exponential distribution, and the plot looks like skewed. The first plot looks like a skewed normal distribution, where you have when the parameter sigma is 0.5, you get the mode at 0.5. And when sigma is 1, the maximum value occurs at 1 as well, and then it goes on. So A sigma is increased. It's more flattened. Okay. There are a lot of applications which cannot recall at the moment. But you can look at more information about this distribution on the Wikipedia page. Okay, the second question is similar to last week's. When you are given the PDF, how do you compute the CDF, which is the cumulative distribution function? The CDF is computed using integral over from the last point, that is 0, up to a given value X. You would integrate your PDF. In this case, if you integrate with respect to t, it's t sigma squared times e to the power minus t squared divided by 2 sigma squared. Okay. How would you integrate this? How would you integrate this? What would be your method for integration? Thanks, Kai. Yeah, you would use substitution. I use substitution, which is easier. You could also try using by parts. But when I use substitution, these two terms, the first fraction cancels out. Okay, let me show you that. I need. Please, on Monday, have a look at the update on GitHub. Okay, I usually update with all full solutions later on. Okay. Okay. By substituting u equals t squared, like t squared divided by 2 sigma and deriving u with respect to t, I got dt is sigma squared t du. So just putting it in here, t sigma squared e power minus u, and instead of dt, that's sigma squared over t du, which simplifies to e to the power minus u du, which is equal to minus 1 e power minus u 0 to x. So that's equal to 1 minus e power minus x plus e power 0, which is 1. So rearranging this, we could get it's 1 minus e power minus. Oh, I forgot something. So this is when when t equals 0, you should get u equals 0. When t equals x, your u equals x squared over 2 sigma squared. So these bounds should be changed. X squared 2 sigma squared. Which is equal to, so that's minus x squared 2 sigma squared, and 0 otherwise if x is less than 0. Okay, is that the PDF? Yep, that's what we wanted. And in the notebook, you can use Mathematica to find this integral exactly. Yeah, I'll show you how to do that. Okay, so suppose fx is equal to the PDF given, and then you can use the integrate function to compute the definite integral, or without the definite integral. So the CDF is given by 1 minus, because I've used u here, that would be 1 minus e to the power minus u 2 sigma squared, which is what we wanted. Okay. Question 3 is show that fx is, that is the PDF is a valid probability density function. By showing that the integral over 0 to infinity is 1. Again, you could check this using Mathematica by using the integrate function, or you could use numerical approximation to compute this. When sigma is 1. Okay. Numerical approximation use this like Riemann integral sums. Okay. But you should be also able to show this by hand calculation. Okay. Let me show you the hand calculation. Okay, this is the question. We need to show that the PDF is integrates out to 1. That shows that it is a probability density function, which is proper. Okay, to do that, you would again take the function, PDF function, and evaluate it, integral, this time from 0 to infinity, which is the entire region. That could be done by, let's say, first take 0 to y, and then we would take limit whereas y goes to infinity of this integral. Okay, noticing that this part, this integral is the CDF, okay, which we already computed. That is 1 minus e to the power minus y squared divided by 2 sigma squared. And as we take the limit, as y tends to infinity, we get 1 minus 0, which is 1. So that shows that it is a probability distribution, which is proper PDF. Okay. The next question I've asked is, show that the mean. Okay, question 4 is show that the mean of x is sigma times square root of pi over 2. Remember last week, we have defined mean as expected value of x, which is computed by using x times the probability density function. You would integrate that over the range. Okay, in this case, it's x times the PDF of x, the Rayleigh distribution. How are you going to compute this integral? Oh, Kai has asked 2 questions. Example, let me check an example. I had it before. Okay, can you think of how you would integrate this? Yeah, you can use by parts. So that's the answer to your question. One example is in communications theory, to model multiple parts of dense scatter signal reaching a receiver. Another example is in physical science to model wind speed. You could also use in medicine. Image to model noise variance in magnetic resonance imaging. Okay. Yeah, we are going to use okay, I'm going to give you another example. In engineering as well. Okay, to find the mean of x, okay, it is x times the PDF, integral of x times the PDF of fx, which you could use by parts if you want, but I've used substitution again. If I let t be x squared divided by 2 sigma squared, and then I got dx is sigma squared over x dt, so I could cancel this part here. Then x can be written as square root of 2 sigma squared t, which is because sigma square root of 2 sigma is a constant, you can take it out of the integral. And then what is remaining is t to the power half e to the power minus t. Okay, you could still use integration by part if you want, but I am familiar with gamma function, so I'm going to use that. Okay, a gamma function is defined as t to the power x minus 1 e to the power minus t dt. So that's the definition. Okay, applying that in our case, we have t to the power half. Half can be split as 3 over 2 minus 1, which I've done here. And that is really gamma 3 over 2. And using property of gamma function, we have gamma x plus 1 equals x times gamma x, and gamma of half is a square root of pi. Okay, so the first part is splitting this half into 3 over 2 minus 1. So I could apply gamma function, which is gamma 3 over 2. And gamma 3 over 2, it can be written as gamma half plus 1. And using this property here, I've said that is gamma half. That's half times gamma half, which is half times square root of pi. Okay, that's sigma square root of pi over 2. Okay, so that's the mean. Okay, you could try using integration by parts. Okay, there is no harm in it. Any questions? All right, no questions. The next question I've asked is find the variance of the Rayleigh distribution. Okay, the variance. Okay, remember from last week, variance is expected value of the second moment, which is x squared minus mu squared, and then expected value of x squared can be written as, so this is really expected value of x squared, can be written as x squared times the PDF. That's the PDF, fx, dx. Now this time, the integration, I'm using by parts. Okay, using the by parts formula, I said let u be x squared, and then du is 2x, dv is the rest, x divided by sigma squared equal, that's the PDF. Okay, and finding v is, to find the v, I use substitution, and I've got up to minus e power minus x squared divided by 2 sigma squared, that's v. So putting it into the formula of integration by part. That's the next step. That plus that. From the first part, that is 0. And Second part, we need again integrate x equal minus x squared 2 sigma squared. For this part, I've used substitution. Okay. That gives me, after canceling everything, that gives me integral of e to the power minus u. And this 2 sigma squared is outside, and integrating this part again gives me minus e power u, which when I evaluated with limit is x goes to infinity and x goes to 0, is 0 minus 1, which is 2 sigma squared. Okay, and that means computing variance using the formula variance of x is equal to expected value of x squared minus mu squared, which is mu. Mu is the mean which we computed earlier, with that is sigma times square root of pi over 2, which simplifies to sigma squared pi minus 4 divided by 2. Okay, is that what we wanted? So it's the other way around. Somewhere I made a mistake. Okay, check. Yeah, 2 sigma squared. That's what I got for the second moment. 2 sigma squared minus. Yeah, it was this part, simplification, I made a new. So that's the real calculation. Okay, any question for that part? All right. That's computation of variance. Now let's have a look at the rest of the question. Okay, I will be filling in the solution here, but this part I have put the code here just to make sure that when you do your assignment question, you could check whether your work is correct or not using Mathematica. So the second moment, this is how I computed the second moment, where fx is defined previously. Assuming sigma is positive, I got 2 sigma squared. And you could use this to compute the variance. You could also use n integrate, which gives you a numerical approximation to the integral to compute the integration as well. Okay, I think one of the questions you are required to do this. This is the same thing as the n integrate, where you compute the sum, that is Riemann sums. Okay. So variance is given by this formula. Okay. I hope that's clear enough. Is there any question from this part? Hi, to your question, I haven't really dealt with this probability density function in like in application, so I'm not sure about that question. Okay. This is for you guys to know the properties. Okay, the second part is about simple linear regression problem. I remember discussing this in the very beginning, maybe for your assignment one. This in this problem, you have some data points. The aim is to seek parameters b0, b1 to fit the line y equals b0 plus b1 x. b0 is this is like a straight line equation. b0 is the y-intercept. b1 is the slope. You seek these parameters by an optimization problem that is minimizing the loss function. In this case, the loss function is yi minus your yi's are the observed values minus these are the predicted value. This is the predicted value from the model. And in this case, the first question I've asked is compute an expression for the gradient of the loss function. How would you compute this? Yeah, you would use partial derivatives here. Could you try to compute it? And let me know what is the derivative with respect to beta 1 and beta 0. Okay, is that beta 1 or beta 0? Hmm. Yeah, you're right. So I hope everyone else knows how to do this. And how would you apply gradient descent algorithm for this problem? Have you learned about it? How would you use gradient descent algorithm to seek beta 0 and beta 1, which minimizes the loss function? Yeah, find the step. Yeah, direction comes from the gradient. That's good. Okay, let me show you. Okay, I think I've explained this before, but let me try again. So in this model, y equals beta 0 plus beta 1x. Y is the dependent. So this is independent. This is the dependent variable. Okay, there is a mistake here. And beta 0 is the y-intercept, beta 1 is the slope of the line. So what happens is, if you're given data points of scatter plot of the data points, the aim is to find a line which minimizes the error, okay, these errors. For what would be that beta 0 and beta 1? Okay. You could use the loss function is described, but if you use gradient descent algorithm, the first step is you could choose initial values, beta 0 and beta 1. Let's say 0, 0. Okay, then choose the step size or learning rate. Okay, it could be a small value, say, for example, 0.01. Learning rate gives you the rate of speed where the gradient moves during the descent. Okay, setting it too high may result in invisible paths. Setting it too low may result in slow convergence. Okay, and the steps are in step 2, you would compute the partial derivative of the loss functions, which is like partial derivative of the loss function with respect to beta 1 is the derivative of the sum with respect to beta 1. And using the property that derivative of the sum is the sum of the derivatives, we could compute it by using chain rule. Is minus 2 times the sum of xi times yi minus the predicted values. Okay, similarly, beta 0 is again using chain rule. We compute the partial derivative, which is minus 2 times the sum. This time it's yi minus the predicted value. Okay, now then in step 3, you would update the current values of beta 0 and beta 1 using, this is the previous step value. That's the previous beta 0. Okay, and you would update beta 1 by beta 1 minus the learning rate or step size times the derivative of beta 1 and the derivative with respect to beta 1. Okay, that is db1, and beta 0 is similar. And you would repeat this process until the loss function is very small, typically 0. Okay, so that's the gradient descent algorithm. You are asked to simulate, you are asked to fit this model to some given data points using gradient descent algorithm. Okay, so those are the steps. Okay, any questions? Why would it converge slow when loss is small? Okay, that makes sense. Okay, in the rest of the preg, I'll give you time to ask questions from assignment. The individual time is also okay. So let me stop the recording so that I can give you help with the assignment.